All right, so this is our last video. It's putting it all together. So we have simplifying. We did that. We did U substitution. 3 different videos of a lot of U substitution. There's a lot that we've done with that. And then we also have integration by parts. Now, I've done a lot of videos with integration by parts already. There's no difference. It is what they are. So if you want to review those, you can go back. But what I did pick right now is this one problem that's going to use all of this. So we're going to put it all together and to show you that they are steps where you really want to look, can I simplify? Can I substitute? Can I integrate? But they're also just steps. So you can actually say, can I integrate with parts? Can I do substitution? Can I simplify? So if we look at inverse tangent, the first thing we want to do is go to our table and get an idea of what we're looking for. So what we have for inverse tangent is a derivative, and that's a hint that we're going to be using integration by parts because we're going to be taking the derivative of our inverse tangent and getting 1 over 1 plus x squared. So that's what we want to write down, is that one. So that is our goal, to be able to use that. So the derivative of inverse tangent of x was 1 over 1 plus x squared. So now what we need to do is we want to clean it up because we don't want to do integration by parts with a radical x in there. That's going to introduce chain rule. So we want this to be a nice t or some other letter here, like b or something. So we don't want to use u because we're going to use integration by parts, and u's already been taken. So what can we do here? Well, let's call it t. How about that? Tangent inverse of t. So now we know that we're going to set our t equal to radical x. But if we take the derivative of a radical x, it's going to get really messy. It's going to give us a half over radical x. And it would just be nicer to say, well, why don't we make this nicer and say t squared equals x. So if we square both sides like that, we end up with something that's nicer to take the derivative of. So that's 2t dt equals dx. And this gives us something nicer to plug in. So this would now be times 2t dt. And now we can see that this is our u and this is our dv. And why am I picking this to be the u? Because that's the derivative that we have. So if I say u equals inverse tangent of t, that means du equals 1 over 1 plus x squared. And my dv is equal to 2t dt. So my v is equal to just plain old t squared, which is nice. All right, so now we go t squared inverse tangent t, and that's done, right? We still have to plug in the radical x at the end, but that part's done. So now let's see what we have left. Oops, forgot the dt. It always tells me when I need it because it's going to be v du. So this becomes, got a mistake here too. This should be a t squared. See, I plugged it in, but not there. See, everything needs to match. So it'll tell you when you make little tiny mistakes. You just have to be aware of them like that. And then now we're ready to go. We've done these before, so we can use trig substitution. We can do long division. In fact, why don't we do both to show you that they both match? So I'm going to highlight this so that I don't forget it. And then we're going to take the negative. We'll leave it to the end. We're going to do just integral. Let's highlight the negative so we don't forget that too. All right, integral of t squared over 1 plus t squared dt. And then I'll put some space over here, and we'll do the same thing. So which one do you want to do first? Like, you could tell me. But we have dividing or we have trig substitution. Let's do trig substitution. So we know this needs to be a 1 plus tangent squared, right? So if you go look at your table, we have a square and a square, so we got to do x equals a. So a was 1, so it's going to be x equals tangent theta. It won't be x, though. And we're trying to get 1 plus tangent squared so we can make it a secant squared. So we want our t to be tangent theta, so that dt is equal to secant squared theta d theta. So when we plug this in, we get tangent squared theta over, and I'm going to make this nice and quick. That's tangent squared, and then dt is secant squared theta d theta. Now we know that the bottom is secant squared, so that we can just cancel with the secant squared. There's no need to simplify it. And then we have tangent squared d theta. And we've dealt with tangent squared many, many, many times. That's just secant squared theta minus 1. And then that becomes tangent theta minus theta for our problems. Now, we have to replace it with the t so that at the very end, we're going to get t squared inverse tangent t minus this, right? So we've got to come back and go, okay, well, if tangent theta equals t, that's our first one. So that's t minus, and then theta would be inverse tangent t. So now we know this is t squared inverse tangent t minus t plus inverse tangent t. Now, we still need to plug in that radical x from the very beginning because t is equal to radical x. We started with x, we need to end with x because this is not a definite integral. So we just replace the t with radical x. So that would just become x. Radical x minus radical x plus inverse tangent radical x. And there we go. Oh, plus c, plus c, plus c. Got that constant. All right, so that was one way of doing it. The other is long division. So if we go back and we're going to, hopefully you've got that one down. Let's look at the next one with long division. So our top is t squared. So remember the degrees, if they're greater than or equal on the top, then we can use long division or synthetic. So this is t squared plus 0t plus 0 divided by t squared plus 1. I just switched them. So this would be 1, and we end up with t squared plus 1. Change the signs. So those cancel, and we end up with negative 1. So our quotient was 1, and then we had a remainder of negative 1. I'm going to put it as t squared plus 1 dt, and then that should look really familiar. So we already know that's t, and then if we go all the way back up, we already knew that the integral of 1 over 1 plus x squared is inverse tangent. So this is minus inverse tangent t plus c. So it was actually a little bit nicer than doing all that trig. All right. Oh, that looks horrible. Let's do that again. You can make it nice on your paper. We'll do a squiggly line there. A squiggly line there. All right. So now if we plug in the radical x, right, that becomes radical x minus tangent inverse radical x plus c. And then we just attach it on to our very beginning one. So you can see that radical part became the same thing. When we finished it, you can see there's my t minus inverse tangent t. There's my t minus inverse tangent t. They both worked. So what I'm trying to get at again on all of these is to just try stuff. You just try it. If you sit there and stare at it and think that it's going to come to you, it's not. You have to sit there and just try things at it. So you try simplifying. You try U substitution. You try integration by parts. You just try stuff. So if we had just tried this as well, here's another one. If I just said, well, that's my u, inverse tangent of radical x, and my dv is dx, and then I have to use chain rule, that's fine. So I end up with this times this, that's our first part, and see it matches. There it is, x tangent inverse x, and then we end up with this times this, and so that gives us this. Well, then we go back and we actually do what we were going to do from the very beginning, and that's to put the t equals rad x into it. And it works with this, it gives us this, and look, there's my integral. Same one I had here, same one I had here. So it didn't matter the two steps. I did a U substitution after my integration by parts, and here I did the U substitution before the integration by parts. Gave me the same exact answer. The whole point, again, is to just try stuff. So don't be afraid of these. Give yourself time to work them out, and write down what you did every single time you tried it. Use the notes, use the formula pages.